A very warm welcome to everyone. Now in this video we will be exploring the calculations of electric fields due to continuous distributions of charge. In our previous video on electrostatics, titled Electrostatics 4, we discussed electric fields due to systems of point charges and dipoles. In this video, we are dealing with continuous distributions of charge. Now, when you have continuous distributions of charge, like for instance, you have a ring of charge, or you have a straight thread, long straight thread carrying charge on it, the electric fields will still be calculated by breaking up this continuous distribution of charge into tiny point charge elements. And those tiny point charge elements are then considered, and their fields are calculated, and then we do a summation of those fields. Now the description may not make it very clear to you, so what we are going to do is try and understand this with some actual examples of field calculation due to continuous distributions of charge. And the first example of this that we will take is that of a uniform circular ring. Now let's say we have a uniform circular ring having a radius r kept in the YZ plane. This is y-axis. The x-axis is the axis of the ring, and the z-axis is perpendicular to the plane of this board, and the ring is kept in the YZ plane. And since it's kept in the YZ plane, it kind of appears like an ellipse here. And we are interested in calculating the electric field due to this ring at a point on the axis of the ring. Let's say we have at a distance x. The ring carries a charge q on it, and this charge q is distributed uniformly all over the ring. Now at this point here, we are going to calculate the electric field of this ring by dividing the ring into tiny little elements carrying a tiny amount of charge dq. We are going to take very tiny, very small elements, and the reason for doing that is that we actually know how to calculate the electric field due to a point charge. So we need elements that can be approximated to a point charge, and then we calculate the fields due to those elements. Once we know the electric fields due to all those elements, we will actually do a summation of those fields and eventually calculate the resultant electric field. Now with this ring, what we are going to do is, as I said, we will consider tiny little elements, and let's say the first one of those elements is over here, and this element, let's say, has a charge dq on it. Now let's consider the field due to this charge at this point. Now the distance of this point from this point charge is root of, this is a right angle triangle, x and r, so this comes out to be root of r square plus x square uh, the angle here is, let's say, theta. Okay. Now, of course, the angle theta is pretty much known because we can, from this figure, we can calculate its sine and cosine. The cosine of the angle theta, for example, is x divided by root of r square plus x square. We're going to require this a little later, so we have calculated it already. Now, we're interested in calculating the field due to charge dq at this point. To do that, we need to know the distance and the charge. We know both. I'm assuming this charge on the ring to be positive, so dq is positive as well. The electric field due to dq, therefore, will be pointing radially away from dq, and this field dE will be equal to 1 by 4 pi epsilon naught dq by the square of this distance. Now, the square of this distance will be r square plus x square. Right. Now, we can actually use the symmetry of the situation to simplify the job for us. In general, these electric fields of magnitude dE each due to all the elements will be in all kinds of directions. And when we do a summation of vectors, we have to do a summation of x components, y components and z components separately. And that would be a long, tedious task. But then we are helped by the symmetry of the situation here. For instance, if you consider a diametrically opposite element here, having the same magnitude of charge dq, then the electric field due to that element would be this way. It would have the same magnitude and it would have this direction. Now, the angles would be same here and here. If this is, theta, this angle is theta as well, and similarly this would be theta. Now, the components of these two elemental electric fields, these two dE fields, they're components which are perpendicular to the axis of the ring. This x-axis is the axis of the ring. The components of dE which are perpendicular to the axis of the ring will be equal and opposite. The dE sine theta component for this one, dE sine theta component for this one, these ones here, dE sine theta. Similarly, we have dE sine theta here as well. These two cancel out. Now, the same thing repeats for all field components which are perpendicular to the axis of the ring. So, whenever we take a pair of diametrically opposite charge elements, the field components which are perpendicular to this axis of the ring will be dE sine theta each in exactly opposite directions. So, they all cancel out. Therefore, for all such diametrically opposite elements of charge, the electric fields or the electric field components which are perpendicular to the axis of the ring, they all cancel out. Therefore, the net electric field will have a zero component perpendicular to the axis of the ring. If here, for instance, the axis of the ring is the x-axis, then electric field perpendicular to the x-axis will be 0. And therefore, the net electric field will have to be along the x-axis. Now, this net electric field will be a summation this net electric field will be a summation, that's an integral, of the x components of all the dE elemental fields. So the x component of dE will be, of course, dE cos theta. Now what you need to do is to do a summation of dE cos theta. This summation of dE cos theta along the x-axis direction will give us the net electric field. Now let's substitute dE over here and also cos theta, and let's see what we get. The net electric field now, E net, will be equal to the integral of dE, that's dq, by 4 pi epsilon naught r square plus x square times cos theta, which is x by root of r square plus x square. Now what we can do is, because x and r are constants, they come out of the integration, and your net electric field will be now calculated as x by 4 pi epsilon naught r square plus x square to the power 3 by 2. R square plus x square into root r square plus x square is r square plus x square to the power 3 by 2 times the integral of dq. Now that becomes a very simple integral. If you're adding up, you're doing a summation of all the values of dq, then you end up with the total charge q on the ring, and therefore this net electric field comes out to be 1 by 4 pi epsilon naught times q x by r square plus x square raised to the power 3 by 2. Now this is the general procedure we will be using for calculating electric fields due to continuous distributions of charge. This is the first example. We have covered the example of a circular ring. The electric field due to a circular ring of charge at a point on the axis of the ring is given by this expression here, and it is directed along the axis of the ring. Of course, I have assumed a positive charge, so the field is pointing away from the center of the ring. So if you have a ring like this and you're looking at the electric field here, it will be pointing away from the center of the ring if the charge is positive. And if the charge on the ring happens to be like negative, and you're looking for the electric field here on the axis of the ring, then the field will be directed towards the center of the ring. So for a positively charged ring, the field points away from the center of the ring. For a negatively charged ring, the field points towards the center of the ring. So that's the simple example of a uniform circular ring. Let's now take up a slightly more challenging problem where we'll be looking at a very long line of charge. So hopefully you've taken a screenshot of this and made notes. I will now proceed with the case of a very long line of charge. You can imagine a thread of very large length carrying some uniformly distributed charge on it. So this time we are looking at a very, very long line of charge. So we have now an infinite line of charge. This line of charge has a linear charge density equal to lambda. Now what's meant by linear charge density? It is actually the amount of charge per unit length on this line of charge, and we are assuming this to be uniform everywhere on this entire thread, on this entire line of charge. The linear charge density lambda is being assumed to be constant. Now we are interested in calculating the electric field over here at a point which is distant r from this line of charge. Now to do this, to calculate the electric field here, what we need to do is we need to divide this line of charge into lots and lots of tiny little elements. Now we do that in a very interesting manner. We take an angle theta here and draw a line, and then increase the angle further by a small amount, let's say d theta, and draw another line. Now let's say this distance here is L, then this length here would be dl. If this is r and this is theta, this length would be r, this length here would be r by cos theta. Now we are looking at this little element here, this element, which as per the diagram here, this element has a length dl. We will be calculating the electric field at this point due to this dl, and then we do a summation of all the electric fields due to all such elements on the line of charge. Now let's say this L divided by R, this gives us, of course, tan of theta. So L equals R tan theta, and dl by d theta, of course, would now be R sec square theta, and therefore this dl comes out to be R sec square theta d theta. Okay, so we've got dl. The amount of charge dq on this dl would now be the charge per unit length lambda times the length dl, and that of course is lambda r sec square theta d theta. So that's your dq. Now the field due to this dq at this point, again I am assuming the charge here to be positive, and therefore the field dE due to this dq can easily be calculated. We know dq, we know its distance, so dE now comes out to be one by 4 pi epsilon naught dq divided by square of its distance. We are using the expression for the electric field due to a point charge. So the electric field due to a point charge is 1 by 4 pi epsilon naught q by r square. Here in place of q we have dq, and the square of this distance here, that will be r by cos theta whole square, that is r by cos theta whole square. Now remember, 1 by cos theta is sec theta, so 1 by cos square theta will be sec square theta. dE now comes out to be 1 by 4 pi epsilon naught. We substitute this dq over here, lambda r sec square theta d theta by r square sec square theta. Now the sec square theta cancels and r cancels. dE now is equal to lambda times d theta by 4 pi epsilon naught r. Now again, we will be using the symmetry of the situation here. For instance, if we consider another symmetrically located element here, you have an element here at L having a length dl. Let's consider an element again at L having a length dl, this element. Now the electric field due to this element, dE, will be directed this way. The angle here would also be theta. Now you will notice that the electric field components which are parallel to the line, this is, I've drawn a line here parallel to this line of charge. The electric field components which are parallel to this line, these ones, dE sine theta each, dE sine theta, dE sine theta here as well, these two will cancel out. Therefore what happens is, for every pair of symmetric elements, field components which are parallel to the line of charge will cancel out, and therefore the net electric field parallel to the line of charge will be 0, or rather the component of the net electric field parallel to this line of charge in this direction, the net electric field will be 0. The direction of the net electric field will now be in this direction. The net electric field will be directed this way, E net, and this E net will actually be a summation of the component of dE in this direction. So the net electric field is now a summation of, well, dE cos theta. The dE sin theta components all cancel out, dE cos theta components all add up, and the net electric field is now in this direction. So net electric field will be a summation of dE cos theta. So what we get is, we substitute dE here, lambda cos theta d theta by 4 pi epsilon naught r. The limits of integration now. Now we have to do a summation for the entire line of charge. Now for the entire line of charge, we have to consider elements all the way down from infinity to all the way up to infinity. Now if I draw a line like this from here for the element which is at negative infinity below, that line will actually end up being parallel to this line, because only parallel lines go and meet at infinity. I'll repeat the argument. For the element at infinity down below, if I draw a line like this, that line will actually be parallel to this line, because only parallel lines go and meet at infinity. So the line drawn from here all the way up to the element at infinity below will actually be parallel to this line, and the angle theta here would be 90 degrees. Of course, angles above the line are positive, angles below the line are negative. So for the element at infinity down below, the angle is minus pi by 2, minus 90 degrees here, and for the element up above at infinity, the angle will be again 90 degrees or pi by 2. So net electric field now is lambda by 4 pi epsilon naught r. All that constant comes out, and we get the integral of cos theta d theta from minus pi by 2 to plus pi by 2. Now cos theta d theta integrated gives us sin theta from minus pi by 2 to plus pi by 2, and this net electric field therefore becomes lambda by 4 pi epsilon naught r sin pi by 2, that's 1, minus sin minus pi by 2, that's minus 1, and so we have net electric field equals lambda by 2 pi epsilon naught r. Now we made the assumption that the charge on this line of charge is positive, and the electric field now is radiating away from the line. The net electric field will be perpendicular to the line of charge and will be directed away from the line of charge if the line of charge is positive. So for a positive line of charge, the electric field is directed away from it and is perpendicular in direction to the line of charge. And if we have a line of charge with a negative charge on it, the electric field will be directed towards the line of charge, but will still be perpendicular to this line of charge. So we've looked at in this session here, we've looked at the electric fields due to a ring of charge and an infinite line of charge. In some of our upcoming videos, we'll be looking at electric fields due to some other kinds of charge distributions as well, and arriving at these results for some more interesting cases of electric fields due to continuous distributions of charge. Thank you very much for watching this video. Do let me know in the comments whether this was completely clear to you or not, and if you lack clarity anywhere, please do not hesitate to ask, and I'll be happy to clarify in the upcoming videos. Thank you very much for watching.